Hello everyone, I'm Mahsa Safarkhani, PhD student at the topic of ambient signal as a tool to characterize material properties. I have a light in talking about my project and the main goals of my project and the method we want to use. In the recent years, ambient seismic noise recorded has a valuable information for the studying the earth material and structures. And the main assumption would be that the cross correlations of the signal from two receiver recording at the same time yields the empirical green functions between station pairs. And there are some assumptions in this studies, empirical studies related to the uncorrelated sources and uniform noise source distributions and equipartitions of the energy. And also the seismic noise tomography have a several advantage regarding to the surface wave tomography, including the independency from the occurrence of the earthquake or performance in the shorter period. But we know that in the real world conditions, actually the distribution of the noise sources is not uniform and anisotropic. In this issue caused that the cross correlations convergence to the empirical green function partly or not at all, or we can bias by azimuthal energy flux. And in addition, ambient seismic noise cross correlation are being used to detect the temporal variations of the seismic velocity and temporal variations in the properties of the noise sources can cause in the change of the apparent velocity, including, for example, the spatial distributions and frequency of the ambient noise have a seasonal variation due to to the variations of the or seasonal hemispherical shift to storms. So investigation the effect of the noise sources in cross-correlation signals is a critical issue in the further applied noise-based study, for example, imaging, monitoring, and the other application for the retrieving the accurate results. So the data we use in this study is that the large array in the region closely in the Vienna and extremely close space, including the 1,000 stations. And also there are a lot of type of sources generated seismic signals, including the terrain, microseismics, and also wind parks. So we are able to detect the locations of these kind of the sources and also investigate the effects of the different type of the sources on the noise correlation functions. So first, we want to find the location of the noise sources. So we use the beamforming methods. In these methods, we investigate the differential of travel time of the plane wave from coming towards the seismic array regarding the specific slowness and also the back azimuth. In this method, we are able to, by delay and some methods, find the best delay time regarding the reference station which signals reach to this station, and applying this best delay time to all the stations and shifting stacking together for the improving the amplitude, including the coherence interference of the signals. And so we are able to, by these methods, investigate the direction of the energy coming through the seismic array. This is the result of the three-component seismic array for the Grafenberg station array in Germany, including 39 seismic sensors and aperture size of 100 kilometers, 30-minute recording, including the occurrence of the earthquake in Greece. And as we can see, besides the direction of the earthquake, we have the direction of the energy from the north and west regarding the macroseismic, primary and secondary microsites, and in the central of Europe and most of the dominant macroseismic noise sources are located in the coast of the Scotland and also the Norway. We believe that the better understanding of the spatial temporal noise source properties is a critical issue for the accurate and reliable passive monitoring. So we would like to locating the sources by different observational tools like beamforming and optimizing them, and answer to this important question, how we can compensate the effect of the coherent sources in the ambient seismic noise for understanding the better for the noise generation mechanism, especially macroseismic, and how we can correct in this adverse effect for the better result for the applied studies. Thank you for your consideration.
Thank you.